So first we're simplifying exponential expressions, and obviously we want to work from the outside of the bracket in. So we're just going to be multiplying those into each value. And then as you see on the outside of both brackets, there's a 1. That's just like a little trick question because it actually stays the same. So now we can follow the quotient rule and we can subtract these two similar exponents from each other. So we have two y values and two x values. And once we do all of the subtracting, we end up with this, which we can definitely simplify. And so it's basically x squared minus x to the power of -1, which just gives us x to the 1. And adding our y exponents together, we get xy to the power of 10. Here in the next one, first we're starting with the exponents, and we are adding those together, which gives us 1. So we don't actually have to write that because we know it's to the power of 1 if there's no exponent. And then we are just adding 3 and 2 together, which is 5. And then when it says the square root of 4, we don't want it to look like that. So we are actually going to put it in exponential form. So we're just like breaking this down basically, and 2 to the power of 2 and then to the power of half is the same as the square root of 4. And here I'm just showing that how I typed it into my calculator to get the answer. So we can use a radical with an odd index even if the number is negative. So first we are breaking up the fraction, and we're going to say 1/3 and then to the power of 2. I remember that I had to add my equal signs, and I don't want to lose marks for not putting my equal signs, so I just did that really quick. So the number at the bottom of a fraction is also the index of the square root, and so we're going to flip that and put that as the index and then to the power of 2 still. And the answer I got was 11.9. So for this next question, it's transformations of exponential functions, and our key points we're going to be using is 2 and 1, x and y, and then here we have our formula in g of x form. So first we're going to be graphing it in f of x, and so we are just plugging in that x exponent value, and we are going to be working up from 0 to 3 and then -1 and -2. And we can just plug that into our calculator to get our original graph. So now we are taking our g of x formula, and we are also plugging in values on the x-axis. We can have this formula set up in our calculator and just changing the x value each time. So now we're plotting our original graph, and the graph moves by 1. We're just dotting out the points and then drawing the line. And we can see here that our horizontal asymptote is 0 because it approaches 0 but it never hits it. And plotting out our transformational graph, the asymptote would be 4 because it approaches but never hits it. And our a value is greater than 1, which we can see that it is stretched vertically by a factor of 2. As well as the c value is greater than 0, which means it translates 2 units up. So now for the domain and range of exponential functions, we can say that our d value is 4, and which is the same as y equals 4, which means that the horizontal asymptote is 4. This function is all a set of real numbers, so the domain of this function is just a set of real numbers. And then our range is once again a set of real numbers with a restriction of y being greater than 4 because we know our horizontal asymptote is 4, so it never fully touches it. I have no idea why I wrote 3 there. Please pretend it's a 4. Moving on to our second example, we can say that the domain is once again a set of real numbers, and there are no restrictions on this one either. And the range is a set of real numbers with a restriction of y being greater than negative 1.2 because it never touches it. So now we're going to be doing 2 word problems for application of exponential functions. And sorry, my hand is covering here. I'm left-handed. So the formula we're using is f of x equals ab to the power of x, and a is the initial amount, and then here I just wrote that b is equal to 1 plus the growth rate, and then for decay, it's b is equal to 1 minus the decay rate. So the word problem that I did is, in 2005, there were 57 elephants. Population grows 4% every year. How many elephants are there by 2012? And I am saying let t represent amount of elephants per year. So t represents time per year. So first I want to find out how many years is between 2005 and 2012. So I'm just subtracting the 2 from each other, which equals to 7 years, which we can now add into our equation. And so now that we know the amount of years, we can write ET is equal to A, and then we see in the equation that it is growing, the population of elephants is growing, so we know that it's growth rate, so we do 1 plus r to the power of t, as in time. And then filling it in, we know that A is the initial amount, so the initial amount of elephants is 57. I'm so sorry about my hand covering this. I was trying really hard, but it's not possible. And so anyways, now that we plug in t is our time, so 7 years, and then the growth rate is 4% each year. So that's what that is saying. And then we can go plug it into our calculator. And what we get is 75. So then we write a therefore statement to say what is 75 and how many years. So what I am writing here is from 2005 until 2012, there was a growth resulting in 75 elephants in 7 years. So this next word problem is, a new computer is sold at $3,100. It loses 12% of its value each year. What is the value of the computer after 36 months? So here we have months and years, which we will talk about later on. And just off to the side here, I'm saying let C of t represent the value of the computer amount of years. So now we're saying C of t equals, and we want to check our formula for the decay rate because we know that it is losing value. So it is 1 minus the percentage lost. And then, of course, we have our A value, which is 3,100, which is the initial value. So we have to convert the months into years since the question is asking about years. So we're going to say t equals 36 months times 1 year over 12 months. And we can just cross out the months. And it is equal to 3 years. Now that we know that, we can plug it into the exponent of t, which is representative of time in years. And so now I am just solving it, and we have C of 3 is equal to 2,112.56, which is our answer, so we need to write a therefore statement. So what this last line is basically saying is that the computer value in 3 years is equal to 2,112.56, but we're just writing it a little bit fancier in our therefore statement. As this is a decaying rate, we're saying it drops to this number. So now for finding finite differences, it is basically the opposite of infinite differences. It's where it ends. So in my example, there are just one difference where they are all the same, which means it is the end, but sometimes it can go up to second differences as well, where then it ends. So I'm just doing what we learned a while ago and subtracting the two numbers to get -8.